Hello everyone. This recitation is about the midterm review. Considering that those questions in the upcoming midterm are quite familiar with those questions in the quizzes. So the topic of this recitation is quiz-based midterm review for multimedia course. So I think the materials from the beginning of this course to the midterm can be separated into five parts by the quizzes. So let's first begin to talk about the quiz 5. It was finished on last week. So in this question, you are asked to calculate the likelihood functions of two distributions, distribution A and distribution B. Here we can see that there are A zeros, B ones, and C2s and B3s. And our task is to find the parameter vector A, B, C, D to make the likelihood of the distribution A is larger than that of the distribution B. This is the pattern. This is the Python code. This is just to transform those choices, and then here those two lines of code is used to calculate the likelihood for both distribution A and distribution B. And here, for example, if we observe two zeros, so in the likelihood function, we should multiply. We should to use the 0.1 multiple 0.1, so there will be two zeros. So on the right is this output, and we can use this output to find the correct answer. Oh, this question is quite simple. Yeah. And the third question is about the generating model. In this model, the random variables follow the Bernoulli distribution with a parameter theta. To solve this kind of problem, we just need to use two formulas, the MLE and the MAP. Yeah, actually, we just need to use this conclusion for both the MLE and the MAP. For example, in this question, let's take the choice A as the example. Here, D denotes as the T triple H. So here we can see that N1 equals to 4 and N0 equals to 1. So we can use the MLE formula to calculate the probability of observing a head. For example, it should be 4 over 4 plus 1. It should be 0.8. So the first choice is wrong. Okay, and I also need to emphasize that is in the beta distribution, the first parameter is A and the second parameter is B. And both A and B are related to the priori probability. Yeah, this question. So you have any questions so far? Okay, let's begin. Then from my point of view, I think for the fifth part of the midterm review, I think you need just to know how to calculate both the MLE and the MAP. Okay.
Oh, so for the last question, what was the MLE for that? Is that
A, B are the parameters of the beta distribution. The beta distribution is used for the priori probability. I think this is just the difference between the MLE and the MAP, because in MAP, MAP estimation includes the priori probability A and B.
For like A, what would the MLE for that be?
A equals to 4, for example, this is beta distribution, and A equals 4 and B equals 2.
Oh, and for the choice A, for choice A.
Choice
Yeah.
A.
Yeah, like what would the
Actually, this is for the MLE. It's not for the MAP.
what would the calculation for that be though?
This calculation should be you should use this MLE formula to calculate the probability. So it's not related to the A and B.
So that would be 1 out of 5 then, or
4 over 5. Yeah, because you need to calculate the probability of the effect.
yeah.
Yeah. So in the fifth class, you need to just to know how to calculate the two kinds of estimation, MLE and MAP. And actually, you just need to use this conclusion. Very simple form of the both the MLE and MAP. And then let's talk about the first part of the midterm review. For the first question is related to the concept class. I think for this kind of question, you just need to know three kind of things. For the first thing is you should know is that if a mistake is made, and then the size of the concept class should decrease. And the second thing is that CG plus 1 is a subset of CG. This means that this means that the size of the CG cannot increase. And the third thing is that the size of CG cannot be 0. It means actually the size of the AG should be a positive number, because in this question there's we know that the C be a finite concept containing the contact class. So there should be at least one element in the CG. So the size of the CG cannot be 0. It should be a positive number. So for this kind of question, you need to know this kind of conclusions. And the second question is about the second question about how to calculate the size of the input space, all possible concepts and conjunctive concepts. Okay, let's talk about one by one. Okay, in this question, there are 6 distinct attributes, and for each attribute there are some kind of different number of values, and we need to use those values to calculate the size of those different items. And the first, the input space. Here we know that we just actually it's quite simple. We just need to multiply the number of values in each attributes to get the input space. And for the conjunctive concepts, there should be both a question mark, it accepts all, and the phi. Phi actually it rejects everything. So for phi plus those values. So first we need to for each attribute we need to plus 1 to the number of the values. So for example, for the color, we get 3 plus 1, we get 4. And for the size, we get 4 plus 1, get 5. So we just need to multiply them together. And there's another one, is the question mark. It accepts everything. So finally, we also need to add this scenario. So we can got this the conjunctive concepts. Yeah, I think there is another thing I need to emphasize is about the all possible concepts. All possible concepts here. It is when the number of the target class changes from 2 to 3, actually the all possible concepts should increase, because there is a definition that all possible concepts can be computed by considering the total number of ways you can cover a set with different. For example, if the number of target class is 3, you need to color those number of ways with 3 colors. If the number of class is 2, you need to use 2 colors. So if you use 3 colors, so the number of the most possible concepts should increase. So this is the reason why the choice C is wrong. And then let's go on to the next question. This question is asking you to implement the finite algorithm. Yeah, here is the pseudocode of the finite algorithm. Yeah, I just want to emphasize that in the finite algorithm, you just need to consider the positive examples. Here, if you come to a negative example, you just ignore it and go to the third step 2. Okay, they tell you just need to consider the positive examples. Here is an example in professor's handout. The malignant means the positive, because we want to find the malignant tumor. So, for example, there is a circular large light. This is different, so it should be a question mark. And this is sick. So the first in the first round we can get a circular large light question mark and sick. And this is a negative example. We just ignore it. We come to the fourth example, and here is the oval. So it's different. So it should be question mark and large and light. This question mark and this sick. So we can finally get the hypersize by the finite algorithm. Okay, and then let's come to the candidate and elimination algorithm. Yeah, I think this is quite different from the finite algorithm, because you should consider both the negative examples and the positive examples. So there is a good example in professor slides. I don't know why. Okay. So for the candidate elimination algorithm, you need to find both the specific bond and the generic bond. So this is the pseudocode for the candidate elimination algorithm. I think maybe it's a little complex, so you may review it after this recitation. So I just want here I want to tell you explain this algorithm using an example. For example, first this is an positive example. So CILARISHTH. So initially the S0 should be set to 5. It should be 5 phase, and the general bound should be set to the question marks. Okay, first when we come to a positive example, then we can get this. We can update the specific bound to this one, and then we come to another positive example, and we should compare the corresponding elements in S and the new income examples. For example, CI equals to CI, LE, RI, SH is not equal to IR, so it should be set to question mark, and TH equals TH. So we can update. We should when we come to the positive example, then we need to update the specific bound. Okay. Then we come to if we use the finite algorithm, if we come to a new negative example, then we just ignore it. But in the candidate elimination algorithm, when we come to a negative example, we should update the general bound. Here, we get a negative example, and because we know the specific bound, so we can. So the generic bound should be different from this. For example, OV is different from CI. So we should know that CI should be in the in the region space, and our SM is not is different from LA. So we know LA this is the general bound, version space. Okay, but Li is equal to Li. Or this BK should not be in the version space. This is very similar. And TH is this is not those two elements are not are different. So we should set TH here. Yeah. And then we get a positive example. The positive example usually compare those two. We can get those two elements are different. So it should be a question mark. And the others are the same. So we can get we here when we get the positive example, we should update the specific bound, and then we also need to revise the general bound, because here, for example, there's a question mark. However, you have a CI here, so it should not in the region space. So you finally can get this in the region space. So I think some question will ask how many hypersets in the region space. So I think to solve that kind of question, you need to list all the hypersets in the region space. Okay. This question. Okay, this for the second part, the first part of the midterm review. I think for this part, you need to understand the change of the size of the concept class C, and you also need to know how to calculate the size of the input space, output concepts, and the conjunctive concepts. And you also need to know how to understand the region space, and also know how to use the finite algorithm and the candidate elimination. Okay, let's go to the second part. In this part, I think those two questions in the gradients, they are quite similar, and they both are related to the perceptron, the basic idea of perceptron. It's quite straightforward. The only problem is you need to be very careful about the calculation. Yeah. You have any question? Just raise your hand. Okay. And the second part, this part is about the window. I think this part is about the window algorithm. Actually, this is a pseudocode for the window algorithm. And it includes two parts: the elimination part and the promotion part. In the elimination part, the algorithm will make a mistake on the truly positive example. So, positive example, it means that the true is true. In this scenario, the algorithm will set those elements in the weight vector that equals to 1 to 0. So the total sum of the weights will be reduced. And in the promotion part, the algorithm will make a mistake on the negative example. In this scenario, the algorithm will double the elements that equals to the weight of the elements that equal to 1. Yeah, I think you need to review the window algorithm. And this is a basic idea of the window algorithm. Some questions will ask the conclusions of the window algorithm. So I think you need to review the window algorithm after the recitation. Actually, there is another algorithm is not included in the quiz. But I think you also should be it also should be paid attention to. The algorithm is the halving algorithm. The idea is very simple, and the algorithm predicts the input example based on the number of the positive examples and the negative examples. If the positive examples, the number of positive examples is larger than that of the negative examples, then the algorithm will predict the new put example as the positive. Otherwise, it will predict the new input as negative. If they make a mistake, the version space will be calculated using the previous version space minus this part. So there is a conclusion for the halving algorithm that every mistake results in halving the version space. So for this part, I think you need to do two things. The first one is you need to understand the perceptron, and the second one is that you need to understand the window algorithm and the halving algorithm. Let's go on to the third part of the of this midterm review. Actually, those two questions are quite straightforward. They are all related to the artificial neural network. To solve this kind of questions, you need to use you need to know two things. The first thing is that you need to know how to update the output units, and the second thing is that you need to know how to update the hidden units. Those are the formulas. And this kind of problem is quite simple, but I think the only thing is that you should be very careful about the calculation. For example, because sometimes the question will require you to do about two iterations. So I think it will take a long time for you to calculate it. The idea is quite simple.
Actually, was a question from me for the first one.
For this one?
Yeah, for this one.
Okay.
The error in the hidden node was negative. So can you just show us how it is negative?
Yeah, actually, in this part you may not need you mean sorry.
The error the hidden node 1 or 2, both of them are negative. So can you just show us how it could be negative from that expression?
Yes. For example, in this part, the input is S1 and S2. This is weight. So, for example, the input of the first head node should be 0.35 plus 0.1 times 0.1 plus 0.9 times 0.8. So, and then you put it into the sigmoid function. This is the activation function. The sigmoid function to get the output, and then this output should be the output knows the input. So you can do this kind of.
But I was waiting for two.
Yes, feed forward process, and also you need to use the backpropagation to update those weights. Is it clear? Okay, let's go on. So I think in this part is the idea of okay.
Oh, so those equations there, which one's for batch and which one's for neural network?
Yes.
The neural network's on the left. in the question 2's batch gradient descent, or do you
BS, you mean the BS?
yeah, do you use the same equations for both of those, or is
Yeah,
it-
I think actually I think this is quite simple. So actually you may yeah, actually for the simple node, where you have just two nodes, two hidden layers, two input nodes. I think you just need to calculate it. Maybe you don't need this formula.
so those are all for batch gradient. Those are all for batch gradient descent. Those
No,
are
you
all
don't
for-
need for use the gradient because this is very simple. You have just two inputs and two hidden layers.
If I want to do number 2, I would use those equations though. Not-
Maybe
Or those for 1.
I don't think you need to because you just need there are two inputs and add one base, and there also you also need two iterations. So I think you need to know the results for each iteration. So I don't think you need to use the gradient algorithm.
I have a question. In question 2, how to calculate the square loss value? In the, for example, in the D, square loss value.
This choice D.
Yeah.
Yeah, the loss value is calculated from the feed forward process. Because here you need to be careful. Sometimes it will ask you to calculate the loss value after the certain update. So you need to do because you need to do two iterations. So you have the results for each iteration. So when you calculate the square loss for the second update, so you need to use the results of the first iteration and the updated weights to do the feed forward process.
Would you show me the formula? Which formula should I use?
In this slide, I didn't include the feed forward, but I think the square loss function means the output minus your prediction and to square.
Oh,
Yeah, I think it's very simple.
okay, got it. Thank you.
Any questions?
Yeah, so how do you update them? How do you calculate the error for a hidden node if I have an error at output is 0.2? If say the error at output node is 0.2, then how do you calculate the error at the hidden node 1?
In node 1, you mean the update of
Yeah, how do you calculate the error at the hidden node 1 if the error at output is 0.2?
Yeah, I think this formula gives us some idea of how to update the weights because you know the output, you know your expected value, and you know your output, so you can get a delta. You know the initial weights and you know the delta, so I think you can update the weights. And first, you need to update this layers, the weight in this layer, and then in the same way, you can update the weights in this layer. So this is just the area back propagation process. Any questions? Okay, let's go on. So in this part, I think you need to first understand the artificial neural network, and then you need also to know how to calculate the loss value, and this is for the feed forward process, and also need to know how to update the weight vector. This is for the area back propagation process. I think for this kind of questions, the input, both the input and the hidden nodes will be very small. So I don't think you need to use the gradient algorithm to calculate. Okay, let's go on to the fourth part of the midterm review. And in this part, the first question is asking you to correctly use the Bayes formula. Here is the Bayes formula, and before tell you how to solve this question, I think there is a good example in Professor's handout. Here we know the test accuracy 0.8, and we also know the priori probability is 0.04. And our question is, you will get the test positive. How? What's the probability that I have the cancer? Okay, so that means I need to calculate this. If my test is positive and I have the cancer, the probability of this scenario. So in this scenario, we need to know three variables: the test accuracy, priori probabilities, and the false alarm. After you got those three variables, you just put those three variables into the Bayes formula. You can finally get this posterior probability. And so to solve this kind of question, so you need just to at the first you need to find those three variables. For example, here it gives you this number and this number. So this should be the test accuracy, and this one should be a false alarm. Yeah, and then in each choice, they also give you a priori probability. So you get three variables. Those three variables, you just put them into the Bayes formula to get the results. Yeah, I think this is also quite straightforward to use the Bayes formula. And the second part is about how to calculate the bound of the version space. This formula is in Professor's slides, and you just here. Actually, the epsilon and the delta will be given in the question. So what you need is to calculate the size of the version space. So there's another. Actually, this estimation is quite complex. So there is another way to estimate the complexity of the version space. It is called the VC dimension. Okay, there's for example, whether the points in each figure can be shorted by h. So for the point, if the for any for example in these scenarios, those are two are marked as red and this is as black. So you can use two circles because H is a set of circles. So you can use two circles to separate the different classes. So you can change. For example, you can assume those two are red and this is black. You still can use two circles to separate the classes. So it means that the points in figure A can be shorted by H. And however, in this figure, and if those two points are the same class, and those two points are the same class, and you cannot use two cycles to separate those two classes. So this means that the points in this figure cannot be sharded by the H, by the hypersurface space H. The vector space where VC dimension is equal to the size of the largest subset that can be sharded by H. For example, in this figure, if there are three points are marked as red, for example, this is also marked as red, you can easily use two circles to separate those two classes. And so in this part, I think you need to know first you need to know how to use the Bayes formula to calculate the posterior probability, and you also need to know how to calculate the lower bounds for the version space, and you also need to know how to calculate the VC dimension. Yeah, this I think those are the 5 parts of the midterm materials from the beginning of the class to the midterm. So I think you may need to review those materials separated by different quizzes. Okay, question?
Oh, so can I just ask a question about 2 questions back? That one.
Yeah, that one. Okay.
Yeah, so if I want to get H from that, am I using that 3 to the K plus 1, and K is the number of monotone disjunctions?
No, I don't.
How do you calculate H in that equation?
Equation 3. No, it should be 2 if the dimension equals to the number of the monotone disjunction. It means the size of the version space should be 2 of the power d equals to the dimension. For example, it should be because because you use the binary attributes, so you should not use 3. 3 is about the conjunctive concept. So if you use the binary attributes, so I think the size of vertex space should be if the number of the monotone disjunction equal to the number of dimension, then you can get the size of the version space should be 2 of the power d. D is the dimension.
And then what if they're different?
If the number of the monotone disjunction is not equal to the number of the dimension, then you need to use another formula. It should be virtual. Yeah, in this way. Okay. If d equals to k, we can get that the size of the version hypersize should be 2 power d. 2 of power d. And if the d not equal to k, actually k should be smaller than d. So you can calculate the size of version space should be d k plus d k minus 1 plus d 0. Use this way. Actually, those two are quite similar because because in this way you calculate it should be e plus e minus 0 plus e 0. Actually, eta equals to our power d. Yeah, because it's binary attributes. Any question about the? Yeah, for this kind of questions, I think you need to know which value is the prior probability and which is the false alarm. Yeah. Yeah, actually, the question in the midterm is called the multi-choice questions, but actually there is only one choice that is correct. Yeah. Yeah, I think both the finite algorithm and the candidate elimination algorithm are very important. Do you have any questions? Do you think some other parts are not covered in this review?